Sorry for the being late. Yeah. So, uh, good morning. So I will maybe start on this quantum circuit and quantum gates first. Okay. So, does anyone have a question on what we discussed in the? I mean, this is a very general discussion about the motivating ourselves. What are the things involved when you actually do an experiment? What are the criteria which you should keep in mind uh, about from the knowing a digital computer and any other experimental? And from there, we were trying to motivate ourselves as to what are the requirements which one may have to bear it in mind while making a device based on quantum principles, quantum mechanical principles. So that was what we have discussed, and we'll try to take it forward. So, so anyone has any questions on that about the previous thing? Maybe we can ask before I proceed.
So I have no questions, but I think I get.
Okay. So okay then. So what I don't have that scribble pad, so I'm not able to write and on the go. So I will follow the same technique what I did for your laser classes, and I will take the extract of the textbooks and discuss it. Okay, for this particular section, I'm going to use the book which is a recommended one in your syllabus. It is called as Quantum Computing from Linear Algebra to Physical Realizations. The authors are Mikio Nakahara and Tetsu Omi. So that's the textbook which I am going to follow, and I'm going to use it for the class. So I borrow the. I have not made the PDF file or PPT files. I'm just using the textbook PDF as such, and I'll be discussing uh, more in detail as I understand the subject on that given topic. Okay, so please feel free to interrupt. Sorry. And as I said, first thing what we should know thoroughly for doing this, anything which requires to be done with quantum computing or quantum, any devices or any application based on quantum mechanical principle is that we should understand the implications of the postulates of the quantum mechanics. So last time we saw 2 or 3 postulates and try to interpret it and how will it affect the measurement process. Okay. So before I jump into this thing, I just wanted to highlight one thing. See, in quantum mechanics, we say it is in terms of probabilities. Okay. Now, but for the event which has to happen, it happens with certainty. Either it is there or it is not there. No, that is called a deterministic. So, what is your understanding? Let's say, can you give me any example where you are invoking this probability or you're seeing this probabilistic measurement in action? I mean, you may have read about it. I'm not sure whether you have seen anything or you can visualize if possible. But have you come across any concept which will help you to visualize this probabilistic interpretation of quantum mechanics in any of the subject, whatever you have studied so far? Okay, so what does that mean? I mean, that experiment is about. So can you just elaborate how you interpret that problem. Mhm. So that is just a tunneling problem, right? Yeah. So how do you interpret that as a probabilistic measurement? See, all I want to say is that when I'm talking transition where alpha acting means alpha is some alpha 0 plus beta 1 as a composite two level system where mod of alpha square plus mod of beta square is 1. And when I do a perform an experiment and system collapses into one of the two states. Okay, so mod alpha square or mod of beta square can take any value between 0 and 1 such that mod of alpha square plus mod of beta square should be equal to 1. Right? So it's a closed system where the event has to occur. Hmm. No, no, I'm just asking. I'm not saying what you're saying is incorrect. I'm just, you see, it's a that is also quantum mechanics, right? The event is happening, the measurement is being done. So every measurement quantum mechanically will show that it's a probabilistic measurement. Right? So how do you bring in that concept? Because that is very key to designing any quantum mechanical experiments, any gate, whatever we are going to talk about. Okay, so that will, once you are clear about it, then you will be able to implement any idea or any experiments. You can explore it for realizing the quantum computer, and you'll understand the limitations also posed by it. Mhm.
Hello, Alok. Just one
Yeah.
minute.
Anyone else wants to? I mean, whatever the example which has been mentioned, can you just elaborate on that, or you can come up with some other example where probabilistic measurement is very much apparent.
Alok, can you hear me?
I'm very mild, but yeah,
Yeah, I know. I just sorry to interrupt. I just wanted to ask you.
yeah,
Shall I record this session?
yeah. It's up to you. Yeah.
Okay. Okay. Please go.
Mm. Okay. Yeah. Anyone? Any other interpretation which people want to?
It's a double slit experiment. Like if we
Mm-hmm,
consider photons, then
mm-hmm,
if we send one photon at a
mm,
time, then it's probabilistic that it's a matter of chance that the photon will pass through one of the slits.
correct.
So that is probabilistic. So.
Mm-hmm. Okay.
And
So, and
that
how do you do
creates
that
interference
measurement?
pattern.
It creates an interference pattern. Okay. And so, from that interference pattern, how do you interpret this probability amplitude there?
So actually, its intensity. Intensity is like the electric field mod square.
Mm-hmm. Okay.
So like that's probabilistic because we cannot deterministically tell that through which state the photon has been passing through.
Okay. Right.
So, can I add one thing?
Yeah. Yeah. Right.
So, can I add one thing?
Yeah. Yeah. Sure.
So,
Please.
so actually, this probabilities. what we define it in the while defining the mathematics of the whole system in the wave function, but so it becomes apparent only when we do some measurement on it.
Yeah, that is true.
So
That's right.
so without a ensemble of systems and some collapse happening during the measurement, we can't tell this probability is actually there in the nature.
Yeah, so whatever the result has been collapsed, right? So it will occur with some certain probability,
Yes, sir.
more
Yes.
likelihood.
So we have to do an ensemble of measurements, and
Yeah,
then
after all that you have done, that is what has happened in your interference experiment or your alpha decay. You are able to find alpha particle outside, I mean lower than the threshold value, or some interference pattern on the screen from the double slit interference experiment. So all those are nothing but some process which has happened, and the system has collapsed into one of them with certain probability.
yes, sir.
So how do you associate this probability amplitudes so that whatever the measurements you have done?
So the probability amplitudes are basically like if a wave function is made up of some operator is defined, we get the eigenstates of that operator regarding the system, like related to the system, and then we can deconstruct the wave function using that using the eigenstates of the system, and the coefficients that we get, those are the coefficients squared are the probabilities of each of the eigenstates occurring.
Okay.
So
Yeah, so that is
when the collapse is happening, so it will fall into one of those eigenstates according to the probability given by the square of the coefficients.
yeah. So what is this now in the experiment? Whatever these people have described, how do you interpret this? Collapse has occurred. So something has collapsed into some of those two states, whichever you are considering, and it is measured either in the measurement device for the alpha decay, that is detector there, alpha detector, let's say, and on the screen, if you are using visible light, some you can see a modulation of intensity pattern, dark and bright fringes. So how do you interpret this thing on that?
So I think generally
So it has
regarding
already
any
collapsed. It has already collapsed into it. Okay, so it is collapsed into one of those eigenstates. Now, what is that probability you are going to associate with each of those two, the state to which it has collapsed?
So we can't, I think, using just one experiment, we can't tell that. We have to use ensemble of experiments. Like on the identical systems, we have to do multiple experiments, and then only we can find the probability. Like it will, like the result, number of times the result occurs will determine the what
Yeah, that is what
probability.
the entire interference modulation pattern has occurred because n number of photons has passed through the slits. Okay, he was mentioning about a single photon where he does not know which slit through it has passed through. But definitely, when I mentioned that it has interference pattern created where the intensity modulation I can see on the screen, that means I have done the experiment over a large number of photons, allowed them to be hit on this double slit, and a resultant intensity modulation or interference pattern has been created. Or you are able to detect the alpha particle on the detector. So you have done it over a large number of particles over there.
Yes, sir. So for the double slit experiments, the interference pattern, the dark fringes will give the area where the probability is very low, and the bright fringes will give the probability high areas.
Okay, yeah. So you are coming to that. Anyone else wants to interpret or have some idea about this probability interpretation? See, because why it is important also because we are going to talk about single photon event later. So, and single photon event is very, very tough to detect. It is not that the detector, because detector last time we said that it has certain efficiency. If it is the efficiency of 0.3, which is the normal detector which I use in the normal teaching labs, they are not very extremely sensitive. They are low light level detectors, fine, but not extremely sensitive. So as a result, the quantum efficiency is let's say 0.3. Last time I was talking about 0.3 amperes per watt. That is the sensitivity. Okay. So that means for every 1 watt of light, 0.3 amperes of photocurrent can be generated by the photodetector. So let's assume, or we can talk in terms of the what is the chance that every time the photon is incident on the photodetector, it induces a click. We are assuming there that the response of the photodiode is 1. That for every photon which is incident, you get 1 click, or one photoelectron is generated, which constitutes a current. That is an assumption. But when they say that it's a quantum, that means I require 10 photons to be emitted incident on that detector so that 3 photons can be detected. So if I'm able to measure 3 photons on my as a photo in term photo, if I'm able to detect 3 photoelectrons, which will translate into some number of photocurrent. So from that, if I know the calibration, I can know how many number of photons were incident. Okay. So that is another way of detecting, like every 3. So that is a probability. Probability is for detecting the photon by a detector is 0.3 in the example which I just mentioned. So out of every 3 out of 10 will be detected by the photodetector. The seven are going to go missing. Okay. So if there are large number of photodetectors for a given energy range, so I'm going to detect large number of photoelectrons, assuming that quantum efficiency is the same or linear over the entire energy range. Okay, so that's another assumption which I'm making. So there I interpret that, okay, whatever the detector efficiency, so that is where it is important to know what the detector efficiency, because that is also probabilistic measurement. Okay. In fact, Glauber and Sudarshan have developed the entire theory of photoelectron statistics, counting of it, and yeah, part of it was used, and part of that theory developed by Glauber, who went on to fetch in the what is called as the Nobel Prize. So in terms of the slit, whatever the experiment, the alternate band, so that is the intensity, that is the mod square. So associate either the photon is present means the light should be there. If the photon is absent, light is not there. So the dark fringes automatically says that is the state where the number of photons are going to be low. The photons are not present in that particular spread of the area. But if you know, all of you are aware that the total intensity of the interference pattern is not violated. At the when we see a constructive bright band because of a double slit interference experiment or two slit interference experiment, assuming both the intensity of the incident light through these two slits are equal, then we expect that the bright fringes to be 4 times the brighter than the, or 4 times more intense than the individual intensity intensity of the individual light. That is what we expect, and the dark goes to 0. So this sudden increase in the 4 times increase in the intensity of the light does not mean that the energy is not conserved, because if you take the spread of all the light over the entire area where you can see the interference pattern, that will be more or less equal to the total intensity or the total number of photons per incident per unit time per unit square area will be the same as that is what is incident. whatever is detected on the screen will be the same. Okay. So that means the system has recalibrated in some specific zones on bright and dark photons with certain probability. That is reflected in terms of the intensity amplitudes. The other example which I feel which can give a much clearer insight about this probabilistic measurement is, let's say if you're talking about any two level, like let's say go back and do a hydrogen atom problem. Okay, we know that it has the discrete energy levels n 1, 2, 3, 4, 5, and we are having some kind of a broadly tunable source, or white light is incident on the this hydrogen atom, so it absorbs and re-emits the energy. So if some of you can recollect the experiment or the results of this experiment, they will show that there are certain absorption bands of different colors. Now, if you try to measure the intensity of each of those colors, it will be different. It will not be the same. Okay, I'm factoring into the account, because now what we are doing is let's say intensity is proportional to the number of photons. So the energy will be slightly high. It will be different for different energetic photons. Okay, so that of course will change the intensity, but let's talk intensity proportional to n for a given frequency. So a photon of a particular frequency, and if you calculate the number of photons incident at each of the spectral lines, that will vary. Okay, so what is expected here? That is, expectation is that all the intensities of the number of photons at that particular wavelength should be same. But what we observe is there is a variation. There is a variation in the number of photons at each of those wavelengths. And that wavelength is coming because of the probability distribution. Some transitions are more likely as compared to the others. So therefore, we can safely say that if I'm measuring the spectroscopy, emission or absorption line, that will, the output will be proportional. The intensity will give me the proportional probability of that transition. That is where when we say the Raman lines, in condensed matter, you might have studied this Raman spectroscopy or atomic molecular physics course. We talk about Raman lines, which are extremely weak, very hard to detect. And therefore, what do? To now, it's a routine technique. Why is it a routine technique? Because lasers are available. So how lasers have made you available this access to this technique? Because the number of photons at a given in a wavelength is much higher in case of the laser as a source. So what was available as, let's say, 1000 photons at that particular, let's say, frequency of emission at 514.5 nanometers from a lamp, from the same laser, if I replace the conventional lamp source with the laser source, it is at least 1,000,000 times higher. Okay. So what has happened? So the event was, let's say, with a very efficiency, or Raman lines are very weak, we say, and they are occurring with a probability of 10⁻⁴. So that means for every 10,000 photons, one Raman photon will be executed or will be observed. So that one photon detection is also subject to the detection technique also now. If my photo detector is very efficient with quantum efficiency 1, for every incident photon I get one photo electron, then I can say that okay, 10,000 photons from the lamp will emit one photon. So that will, and then you have to worry about because the photo detector is extremely sensitive, because detecting one single photon is very difficult. First of all, we'll tell you why later when we try to work on physical realization of quantum computers. But there will noise associated with it, dark currents, ambient light will also be following the similar wavelength. So you have to segregate all that. You have to work out some different scheme, which are called as, depending upon the light source, there is a pulse source, then we go for boxcar averaging. If it is a continuous source, then we go for lock-in detection. So different techniques have to be used to make sure that you don't miss out on the photon which is being emitted. Now, if I replace the same thing by a laser source, where the number of photons available is 10 to 6 higher than that of the conventional laser source, the lamp source. So you can see it has improved the corresponding probability. The probability remains the same, but the number of photons which can be emitted as a Raman photons becomes much higher. So that will also be proportionately increasing. The 10 raised to 6 increase is now easily detectable for any photon detector. So even if the efficiency is low, still I have sufficient number of photons so that I can detect the Raman photons. So that is the game of this probability. Probability will be proportional to the intensity, the probability will be related to the amplitude. Here you have to worry about the number of photons which has been detected in that particular energy level for that particular alpha decay process, or the number of photons falling into the, let's out of 100 photons which are fired at the double slit, there is more number of photons accumulated in the brighter region as compared to the number of photons in the dark region. So the probability of finding those photons will be high in the constructive zone of the interference experiment. In spectral lines, we interpret it in terms of what is called as the intensities, proportional intensities. Okay, so that is how we have. So depending upon the experiments, so probability, the point I want to make out is probability is not a very abstract to start with. Okay, so let's say, I mean, if I am throwing a chalk onto the blackboard in front of me, if what is the probability? I mean, you might have done this thing as a numerical example, numerical method course, when you're trying to generate a random number using Monte Carlo simulation. You have a unit circle and then you keep on shooting the number of, I mean, let's say I have a unit circle here in the diagram which I've drawn on the blackboard, and I throw the chalk. What is the probability that it's going to hit the center? So I sum up all the probabilities and the random numbers are generated to certain value. So what we do is we find out the proportional area over the entire region where the chalk has hit the board versus the total area of the board where the chalk is going to hit. So we can know the number of hits and misses. So the area of cross section where the chalk is hitting the board will form the probability. So that is how we work out. So basically, I mean, initially when I was myself a student, I had this very uncomforting idea. What is this probability? Is it really an event happening? How do you measure this? This confusion was there for a very long time till I entered a spectroscopic lab and I tried to understand, and then I got the answer. And I thought I will, that is why I'm insisting to share this answer. I don't know if it's trivial for you or not trivial, but I just wanted to make an emphasis that probability is a very real concept. It is happening every time in the real world. It does have a significance about how the measurement techniques have to be evolved. So what is that we require to ramp up in the experiment such that the event is observable with certain amplitude which is larger than the noise level. Okay, so that is the motivation with which we are going to work. So am I understood? Or did I lose everyone? Okay. Okay. So anything which you would like to comment or ask so that we can move forward?
Sir, I guess that
Yeah.
math center interferometer also is a very good example to show about this probability interference. I mean,
Which
interpretation.
interferometer?
Math center interferometer.
Oh, any interferometer, anything which is working, see, the only motivation is that the experiments are real, and when you're doing at a quantum mechanical scales, you should be well versed with the phenomena which you are trying to emulate or recreate in the lab, and what it involves to detect them with certain higher degree of probability. Okay, you should not miss out on that event. So yeah, Maxent interferometer is routinely used in quantum optics and quantum communications for certain reasons. Okay. Some gates are also evolved based on that. So yes, so that is also an example. Yes, correct. Yeah. Anything else? So anyone from the condensed matter electronics group, does it make sense to you what I have said? I guess not. Anyway, unless until you tell your difficulties, I may not be able to address it. I'm trying to see what I can do from my side. But I require your constant feedback to help me connect with you. Okay, so when you feel comfortable, you can always ask. If anyone wants to ask something? Okay. Okay then. So I'll proceed and start discussing about this quantum gates. So I assume that everything is all right. So let me have this cup of water. I hope it was not very trivial with whatever I have discussed. So is this mode of discussion okay? Or it is too trivializing it? For you, it's okay. Anyone from the non-laser group? How about the PhD scholars? Yes, okay.
Yeah, I'm fine, sir. I'm fine as well.
Okay. You are also saying okay. And the other group, they don't want to comment anything. Okay, fine. Okay, so I will just try to see if I'm able to open starting the presentation. Are you able to see the screen?
Yes, sir.
Okay. So this is a PDF file of that book which I was mentioning, Quantum Computing from Linear Algebra to Physical Realization. So here it's available on the net. If you can download it. There are 2 or 3 sections which are definitely very concise and very nicely detailed. Without going into too much of detail, it gives you nice overview. Though the book is slightly old, but nevertheless for our course it serves the purpose. Okay. So I'm looking at the chapter 4 here. So quantum gates, quantum circuit, and quantum computation. Okay, so people can download this book from there. So before we move forward, our information. Okay, if they are simple, these operations are called as gates. Now that you have introduced qubits to stone, it is time to consider operations acting on them. If they are simple, these operations are called as gates, or more precisely quantum gates, in analogy with the classical logic circuit. More complicated circuits are composed of these simple gates. A collection of quantum circuits for executing a complicated algorithm is called a quantum algorithm, which is a part of quantum computation. So this is the definition which one will be using. So basically what it says is that if I have some operator A acting on a given wave function of an eigenstate, which results into some small a into a psi, so that A operator acting on psi performs some action on that particular wave function, which I call it as a qubit now, because I consider a two-level system there. I'm assuming that that wave function is a composite wave function which has two level. It's a two-level system. So it is acting on that, and that action is called as a quantum gate. If you have more of that in a series way, then we say that we are building up the quantum circuits, just like the way we do it electronically. You build one, whatever the gate, and or XOR, not, then addition, subtraction, all those gates can be built up. And then when you have a series of them, then you call it circuits. So same way we call the quantum circuit. And then if you want to implement certain computation problem in a particular pre-designated way, that is one after the other, not in a random fashion, then we say we are building up an algorithm. And if it is based on this quantum circuit, we call it quantum algorithm. So therefore, a quantum computation, I'm just going through some with me, that's what we are discussing. The quantum computation is a collection of the following three elements: a register or set of registers, a unitary matrix U, which is tailored to execute a given quantum algorithm, and measurements to extract information as we need. So as we last time emphasized, this is all based on your postulates, right? So if you don't do a measurement, the state remains in the superposed states, whatever it's composed of those eigenstates. So it's a collection of the superposition of all those n number of eigenstates, which comprises the physical system. So there is one word which is used here, which is called as a unitary matrix, okay, or a unitary operator. So what is the role of this unitary operator? Why is it required to execute a quantum algorithm? Register is nothing but a set of actions which you would like to carry out, which can be a set of quantum gates. And then we require that those operators or those gates should be unitary in nature. What is that? Why is it required? Anyone can, if you are aware, can they speak out? Yeah. Yeah, please. Uh-huh. Hmm. Mhm. Okay. So that is any transformation. Any transformation vector can do that. So what is so unitary about it? Yeah.
So it preserves the norm, right?
It will
It
conserve.
preserves the
It
norm.
will conserve the. It presents a norm.
Yeah. So
Yes.
that is what
It conserves the.
probability
Yes.
amplitude. So only we.
Okay. So why do we require that norm should be preserved in any quantum mechanical calculation?
so that the probability amplitude remains constant throughout the process.
No, I mean, you're talking about the probability amplitude of an event or overall you're talking? See, I mean, it's if you're talking in terms of vector, it's the length of the vector.
Yes.
Right?
Yes, sir. Yes.
Mhm. It has to be conserved. Mhm. So what is getting
Yes, sir.
conserved and why do you require that? Like we require the wave function to go to 0 as the position vector of that particular variable which defines it goes to infinity. And then mod size square should be finite. It should be between 0 and 1. That is the probability of the given wave function. Probability amplitude. Sorry. If I take integral of size square dx, then that should be between 0 and 1. If there are more than one event, then I say mod of psi 1 square plus mod of psi 2 square should be equal to 1. So why is this restriction of 1 or whatever this conservation?
So
Yep.
can I answer? So the particle has to, like, the event has to be like measured, not measured, I would say. The particle has to be, if you're, suppose
It has to
you're
exist in the real
measuring the
world, right?
position, so
It has to exist somewhere in the real world.
yes, sir.
Only
Yes,
then you
yes.
can measure it. So that is
So
what
within
this.
the bounds that we are given.
Yes. So whatever the
Yes.
measurement, so you define a certain sphere for which you are going to execute some action, and that should be in that what is called as computational space or measurement space. It should be somewhere there. Then only we can talk about detecting it. If it is not there in that particular space, then it's not. You cannot talk about finding it. Right. So that is what is being ensured.
Yes.
Okay, that is the overall system
Also,
has to be conserved. Yes. Yeah.
so also the reason we use a unitary matrix here, because we know by, like, the quantum system, we know that it evolves in unitary transformations, right? So,
What is the significance of that unitary? Because you have unitary operators, you have
I think
Hermitian
I think what
operators.
Ritesh is correct, because, it preserves the norm of the system. Otherwise, the probabilities will be changing always. Like, it will be a time dependent thing. So like, it will be, there will be no like, we cannot even predict the probabilities of it. Rather, even now we can't predict the outcome, but we can predict the probability if you know the psi. But if it is a time dependent
What
thing,
happens? What is it?
and
U dagger U. What does it mean?
so
U dagger U, product of U dagger U. U is a unitary vector or unitary matrix. What does that result into?
I, sir.
I, identity matrix.
Yes.
So
Yes, sir.
it comes back to its original shape. So if I do the inverse transformation, then I should come back to my same state, right? Because U dagger is equal to U inverse,
yes,
right? So U inverse is nothing but is a reversible transformation. So it means that if I have to choose a particular operator which is going to be used for my quantum computational calculation, it has to be reversible in nature. I should be able to. So what does that mean is I should select a set of operators or gates such that I should be able to recover back my original states if I do the inverse transformation. Okay, so that is not required, because if you look at an AND gate operation, you lose the initial states, right? Once the operation is performed, A dot B, let's say 1, 0, the product is 0. So you don't know which of the two states was 1 and which one was 0. So that information of the initial state is lost. So if I have to go back and redo the calculations, then I require this the knowledge of what was that initial states. For that, I require a reversible transformation. Any action which has to be done has to be reversible in nature. So that becomes a very important criteria for me in quantum gate operation. So whether all the classical gates which we know of, can it be quantified or classify itself as quantum gates? That is a big thing, question which requires to be addressed here. I know that I can take any two-level system, let's say a binary digit or based on Boolean algebra, Boolean operators I choose. Whether all those Boolean operators can become quantum operators or can be called as quantum gates. Because some of the operators, but as I said, just mentioned, they are not reversible. So in that case, it does not qualify as quantum gate. But I require them. So how do I go about it? Is there a mechanism of doing it? The other way, trivial way is that, okay, I keep on generating those initial states n number of times as and when required for computation. That means the resource required for doing quantum computation becomes humongous. It's a big requirement. The resources, and it may not be so because you are looking at quantum mechanical behavior, which is very fragile, very at low, happens at very low amplitude, low energy scales. So if you have more of it, then you may lose the quantumness in it. It may degenerate into some classical ensemble. So all those quantum features will be lost. So that is a trade-off. So I cannot do that. So that is where people started asking this question, whether this is possible or not. Then I think Bennett and Toffoli started looking at the conventional gates and found out a way that yes, even if this classical bits of classical gates which are known to us, we can preserve these initial states and perform the operations by adding an extra resource to it. Okay, so what is that resource? That is what we are going to see, which will make the gates to be reversible. If I am able to make that adjustment, then I should be able to use this as a quantum operator or quantum gate. Okay, so what is that? We are going to see that. So reversibility is required to get back to the initial state where it can be reuse it as a different physical resource for a next level of operation on it. Otherwise, we have to keep on, and because you know that quantum mechanical systems are extremely fragile, any action will lead to its collapse or change the original state from a new state. So that will be a problem. So therefore, the moment you have, if you have changed the states of the system, the results will definitely be different. It can no longer be the same. So that is a challenge for quantum computing community. How do we identify those gates and how do we implement and how do we realize them? Okay. So that is what is this game is all. Where reversibility is required, and if you have any other gate, if it is non-unitary, then it picks up an extra phase. So the moment it picks up an extra phase, that means it has evolved into a new state. Because phase is an inherent important property of a wave function. Okay. Okay. So moving on to that. So that is where the importance of unitary matrix is required. Okay. Suppose, yeah. So the hardware one, this is a set of registers along with equipment to control the qubit is called a quantum computer. And a quantum computation is a set H, U, and MM where H is the Hilbert space acting on this complex space of 2 raised to n qubit Hilbert space, a qubit register. And U is again unitary matrix having 2 raised to n operators. So that constitutes what is called as a quantum algorithm, because it's a set of number of instructions given to given system to follow. And then it collapses into a set of measure. MM is a measurement operator to extract in which state it is once the operation is completed. Because we want to know what was that action of this unitary matrix on or unitary operator on the given state, original state. The hardware one along with control is called as a quantum computer. The set the supposed set is fiducial initial states for a unit designed to represent all the on the hybrid connectivity. So the qubit which we have highlighted. So this is slightly more important for us. A qubit may take an arbitrary, so digital computer can take 0 and 1, whereas qubit takes an superposition of 0 and 1, and hence the coefficients are continuous complex numbers. The gate is also an element of relevant unitary group, which contains continuous parameter. An operation such as rotate a specified spin around the x-axis by an angle phi is implemented by applying a particular pulse of specified amplitude, angle, and duration. These parameters are continuous numbers and always contains errors. These aspects might cause challenging defining physical relation of quantum computers. So what is being said here is that, okay, we want to perform an operation such as a rotate a specified spin around the x-axis by an angle phi. So I require to send us kind of a signal. So this is done in this NMR experiment. Okay, so we define some x, y, z axis, and then you want to rotate it. So then that depends upon the frequency, the amplitude of the signal, and the duration, that is the length of the pulse width of the signal, because that is going to create, these are called as pi pulses, if you have to switch off, because you know that, it comes from the definition. Let's say if I have a two-level system, everything is the ground state, and then I want to let the system go into an excited state. So that I can do by applying a pi pulse. If I take a 2 pi pulse, it has to come back to my original state, because that has completed a complete execution of, as is mentioned, that it is a rotation. That rotation is complete over 2 pi on the surface of the sphere, so it comes back to its original place. So therefore, it has to return to the ground state. Okay, so that is what is called as pi pulse in quantum NMR. That when they have to flip the state from the ground state to an excited state, I apply pi pulse. So that means the pulse has to be of certain duration. So that that means I'm supplying the energy for that particular duration, such that all the ground state atoms are excited, are pushed into the excited state, and nothing is left in the ground state. So that is what is as long as the pulse is present. So that is what we say it's a pi pulse. But what will happen if I'm giving a pi by 2 pulse? That means I'm giving half the duration. That means I'm allowing only half the pulse, half the atoms in the ground state. I am pushing it into the excited state, and they are equal in number. So therefore, I have created a superposition of 0 and 1. So that is what this operation is about, and the gate has to be realized. So mathematically, yes, we say it's a pi by 2 pi, but when we are trying to execute in the physical system, it means that I'm applying wave of certain amplitude, certain pulse duration, and at a particular angle with respect to some frame of reference, because the molecules are oriented with respect to the laboratory frame of reference, and that is done by the magnetic field which is being applied there. And it is also to do with the magnetic field or the orientation of the nucleus itself. So that is where this superposition, and it can take any arbitrary value. So that is what this comment is. State upon measurements. When measurements are not made, the time evolution of the state is described by the Schrodinger equation. The system preserves the norm of the state vector during the time evolution. So that is what Ritesh and commented by Sobik, that yes, it preserves the norm of the state vector during time evolution. So therefore, this time development is unitary in nature. So it has to follow this law, U dagger or U dagger U. We will be free from the Schrodinger following and assume there exists unitary of matrices which we need. Physical this is another important second part. Okay, one of the important derived from the unit is that compositional process is reversible. So this is what I have mentioned, that the unitarity of the gate is computational process is a reversible process. So we start with the simple gates. Now this can be a single bit gate or it can be a 2 qubit gate. Okay, so we start with 1 qubit gate. Now this is one thing which is 1215. Okay, this is linearity of any operation is what is we normally in any laboratory measurement. What is that why is this condition for linearity is required? Can anyone who is aware of it can speak out?
Sir, when we say plus some xi1, so let's say x xi1 plus y xi2 equal to 0, one cannot be represented in terms of other. So it has this unique representation, unique basis when it is linearly independent, unique representation of the basis. So that will.
I'm not talking about linear independent here, Ritesh. I'm not talking about linear independent things here.
Okay.
I'm saying that why do you require the measurement technique to be having work only in the linear space?
Sir, I think if the thing is non-linear, so it will have multiple values allowed.
Not necessarily.
Like for example, I'm thinking on the equation side of things. Like if it is a linear equation, it will give a particular value. Whereas if it is a non-linear,
take any example of a linear equation, non-linear equation, and show that it has multiple values.
So not particularly multiple values. What I'm saying is like the evolution is different for both.
Yeah, evolution will be differently. That I agree. But see, the whole point of any measurement system is that there should be one-to-one correspondence, right?
Yes, sir.
For every 1 point, there should be a corresponding 1 point on the other measurement space. So whether it's a linear or non-linear, as long as it is reproducible, it's okay, right? It should be okay, I'm saying. So why do we still insist that we require to do measurement in the linear space? So the linearity has to be done. Yes, so that is the consequence. Yes, that is where that helps us. That the very basis of foundation of quantum mechanics help us to do a measurement in the lab. But here I am talking about the insistent about the why do we require a measurement to be a linear process? Whenever we calibrate any instrument, first we measure its linearity over the range of measurement. Why is that required? See, if you take a resistive element, I'll give you a simple example of electronics, which you must have, all of you must have done it. You have a resistive element and a diode element. Diode element, it will be the, if I look at the IV curve, it will be some kind of a parabolic, I mean, not exactly parabolic, but something like curve shape, which initially decreases slowly and then suddenly shoots up. And of course, I'm talking about the breakdown voltage, anything which is less than that, or the saturation rather. It depends also whether it's a forward bias or reverse bias. Whereas, if I take a resistive element, as long as it obeys the Ohm's law, the IV curve is a straight proportional. So if I take any proportional, so both are now have one-to-one corresponds from the input to the output. Input is my V, I'm changing V, I measure corresponding current. So in both this example, I have a correspondence of one-to-one correspondence. So there is a unique value of I for every measurement which I'm doing with, I'm changing the voltage. Okay. But yet the output behavior is not the same. So as far as my criteria that it should be unique, that is satisfied, but still I don't accept this nonlinear curve measured by the diode to be a good detecting instrument. Whereas I would prefer the resistive element where the graph is straight line, some proportionality constant, y is equal to ix. So that is what I would expect. If you look at the graph, I mean, what is that linear say? It says any proportional change in the input will have a proportional change in the output. That constant slope remains the constant. Whereas if I take a curve, the slope itself is varying. So that means I require to have prior knowledge at where that point on the curve I'm looking, then only I can find out the slope, and hence the calibration becomes difficult for any unknown element. Whereas if I take any unknown source or any unknown quantity which I want to measure with a linear detector, I know precisely that once I have calibrated the entire range, if I know one input, I know what is going to be the output value. Or if I measure the output, I can back calculate and come back and find out what is my input value. Whereas that will be difficult for any nonlinear curve. Okay.
Sir, so basically you're telling that, sir, so basically you're telling that for nonlinear curve, the slope will be different for at different points. But for a straight line, the
Yes.
slope will be constant throughout the
Yes.
thing. So that is the main reason why we are choosing this.
Linear detectors.
Okay, sir.
We always try to ensure that your detection technique is always in the linear range. Okay. Because see, when you are trying to measure this extremely fragile quantities, which are quantum mechanical particles, you have to be sure where is this interaction. As such, you are doing a probabilistic measurement. You are going to lose a lot of information. The efficiencies are not one. There is some dissipation which we have not talked about. Okay. So when we are saying that the whole quantity is conserved, we are ensuring that the system is closed system. It is somewhere in that universe or the measurement space. It is not lost to the environment where it cannot be recovered back. So that is all the dissipative system or open systems. So getting it back to the original state is very, very difficult, or next to impossible. Okay, so those are the conditions why we insist whenever we start a measurement, we have to choose a measurement space or range of space so that the particle will be in one of those. Even if I take a hydrogen atom, there are infinite number of levels practically accessible to it. But I know that hydrogen will be found in n is equal to 1 state. And unless and they give it sufficient excitation energy, then only it can be ionized or it can be found in continuum. If I give a moderate amount of energy corresponding to any of these energy levels which can exhibit these transitions, then those set of finite levels forms my closed system. And I have to ensure that only those range of values of energy should be given such that the system remains closed. So that is where I ensure that my quantities are conserved. So these are things which you have to bear it in mind as we move forward. Okay, so that is with the linearity, and yes, Schrodinger equations are linear. It allows for the superposition of the waves, and therefore, and hence it gives its computing power. Okay. Yeah. So we move on to the next and discuss.
So one doubt, sir.
Yeah, please.
So if the non-linearity is there in these gates, so if does the action of the gate change depending upon the state of the system? Like suppose we give a superposed state of 0 and 1 and we apply the gate to that. So does the
Yeah,
action of the gate itself will change, right?
yeah, because now you are required to know, see the position of that. Let's say if each gate you're applying certain voltage V. Okay, now we don't know where which of this state is in which part of this nonlinear curve, because for some gates I require a smaller voltage, for other gates for other states I require a larger voltage to get the same amount of output. So I don't know which one is going to be applied where. That's the
Okay, sir.
question.
Got it, sir.
Is that clear?
Yes, sir. Yes, sir.
Sir, so does it mean that if it is non-linear, then it is non-unitary also?
Well, that's not the case. Unless and see, non-unitary means essentially you require a closed space and the method has to be reversible. But the fact that most of the unitary operators which you are talking are all quantum mechanical states, and quantum mechanics, whatever you're studying the Schrodinger equation, are all linear, thankfully. So therefore, it will imply that most of these nonlinear operators may not be unitary. I have not worked it out, but this is my hunch. Because I have not thought about this question earlier, but yes. Since you asked, I'm thinking aloud that the Schrodinger equations are entirely linear equations. So any actions are based on that. So unitary will necessarily be formed based on this. And so nonlinear operators may not be unitary. I'll just think more about it and get back to you with this answer. But as of now, my first reaction is that it may not be. Yeah. Okay, so the identity operator. So I'm using a computational basis of these two vectors of 0 and 1 on the two-level system. Okay, and we have this gate operator called I, which is an identity which takes when it acts on this two operator, it will preserve the same state. 0 goes to 0, 1 goes to 1. And the other gates which you for single qubit one or one qubit gates is the Pauli matrices, which someone mentioned in the previous class. Okay, and you can so whenever we have any of these gate, whether it's acceptable as quantum mechanical or not, we have to ensure that you have to take the operation, perform this operation of U dagger U for that particular, and see that you get an identity. So that's the first thing which we should always do. So whenever we define a gate for any action, then that is how we can proceed with the to accept it as a quantum gate. Okay, so we do that this one, and then we find that I of course will end up having an identity matrix. So that is obvious. Then we can choose this Pauli gates, which is X, where it goes from 0 to 1 and 1 to 0. This is also called as NOT gate. And then there are two kind of phase gates, Y and Z, which is y takes from 0 to -1 and 1 to 0, and z will take from 0 to 0 and 1 to, it will negate that -1. So that is the action of this Pauli matrices here, which is, if you take the complete space, it refers here sigma x, sigma y, I sigma y and sigma z, which I define as x, y and z as the gates. So this is the one set of gates which I can apply. And you know why we have defined in terms of Pauli matrices, because we know that Pauli matrices are unitary in nature. Okay. So transformation I is the identity trivial transformation, X is the NOT gate, or called as negation, Z is the phase shift, and Y is a combination of XZ gates. Okay, that is a combination of the negation gate and the phase shift gate. So it's a complex one. So the exercise is that you try to do sigma, take the complex conjugate of all these operators, Z dagger into Z, ensure that it is 1. Okay. And it turns out they are actually unitary in nature. So this is all called a single qubit gates. We'll come to physical system where how we can invoke here. Okay, like X gate, we know that in the example last time we considered was the absorption and emission of light. So you can, that is nothing but it is taking from the ground state to the first state and excited state, and bringing it from the excited state to ground state. So if the light is incident, and if you see an absence of photons, that means it is absorbed. So you know that the system was in the ground state. If the light is emitted after the emission incident of this light, so it will stimulate the action to the downward transition. So it will come out with more light, or it emits more light. So you know that it was in the excited state. So the presence or the absence of the light is going to change the state from 0 ground state to excited, or excited to ground state. So that is where you are flipping the state, and that is the action is called as NOT gate, which was mentioned in the last one. This phase one is slightly tricky, which I'll discuss slightly later when we come to the physical realization. Okay, and how it is evolved and involved here about this transformation. But nevertheless, it is very, very important class. So optically it will be much more useful system. One of the important components is CNOT gate. Okay. What is the CNOT, or called as control NOT? The fact that it is mentioned as control NOT, that means I will try to flip the state based on certain conditions. If and only if the conditions are satisfied under controlled conditions, that this gate will be executed. So that is what is called as control NOT gate. So this plays an important role. Of course, this is just like, I mean, this will, of course, one of the other motivation for examining this gate is we want to find out what is the universal gate which will execute all the other operations. Like you know that in digital optics, you can have the NAND or XOR gate and create every other gate with a combination of them. So that is called as a universal gate for executing digital processing. Okay. So what is the function of this control NOT gate? It is a 2-qubit gate, which where the gate flips the second qubit, which we define as a target qubit, when the first qubit is state is 1. So while leaving the second bit unchanged, or sorry. So I'll repeat again. The CNOT gate is that gate which flips the second qubit, that is the target, also called as target qubit, when the first qubit is, which is also called as control qubit, is 1. While the second bit remains unchanged when the first qubit is 0. So that means only when the second qubit is 1, it is going to flip the state. So since I'm taking a 2-qubit system, which is each one is 0, 1, 0, 1, so the computational basis will be a direct product of those two states. So I will get the basis vectors for this 2-qubit system will be 0, 0, 0, 1, 1, 0, 1, 1. I hope all of you are aware that this is, when I write 0, 0 in this fashion, it means 0 ket into 0 ket. Okay, so they are direct product of those two states. It's a combination of this. So these are the 4 possible combinations in which the system can exist. Okay, so that is the maximum number of possibilities or a combination of different eigenvectors in which the system can exist, and therefore this is also called as a computational basis. Yes. Okay. So, and when you take the state 0, 0, and then when you take a direct product, of course this will be your column vector here. So that is where it is written as transpose. So 0, 0 is defined in terms of this computational basis vectors 1, 0, 0. 0, 1 is 0, 1, 0, 0. 0, 0, 1, 0 is defined for 1, 0 vector. 1, 1 is defined as 0, 0, 1. So everyone is familiar with this kind of an operation. I mean, the product of two direct product of the two vectors. Has it been done before?
Yes, sir. Yes, sir.
Okay. Okay. So now this is my computational basis. Now what I do, I apply this C0 gate on each of these states and implement what the way it is defined. Okay, we say that now this is my first gate here, second gate is this one. So the first gate is what is called as my control qubit, and the second one is my target qubit. So what it says, if unless until the control qubit is 1, only then the first qubit will change. So now the first qubit, second qubit or control qubit is 0 here. So therefore it's not going to change anything. So it remains carry forward the same state of the first qubit. So that remains as 0, 0. So same thing. Sorry, the first qubit here is the control, and the second one here is the target qubit. Okay, sorry, so I'll do it again. So my first qubit is a control qubit. So unless until this is 1, then only the second one will get flipped or changed. So since this is 0, so it will remain, the second state will remain unchanged, and it comes as 0, 0. So same thing is for this one. So again, the control qubit is 0th state. So therefore, whatever the state in which the second qubit is there, it will continue to remain in the same state. So therefore, earlier it was 0, now it is 1, so it will remain as 0, 1. But now when you go to the next one, so you can see that the control qubit has become 1. And then when the second qubit has to flip. So the first qubit will remain as it is, and the second qubit flips to 0 to, it can go only to 1. So therefore 1, 0 becomes 1, 1. Whereas when the control qubit is 1 and the target qubit is also 1, so it is going to flip to 0. So therefore it is going to become 1, 0. So therefore you can see that in 2 of these cases it remains invariant, it remains the same, but other 2 cases it is flipping. So it is something like what is your XOR gate, which is a digital form. Okay, so we'll try to work out that also. So if I can write that, I take the product or the outer product of this one, and then create a computational basis for this entire unitary operation of the C0 gate or the C0 gate operation, so which will be acted on this. So 0, 0, 0, 1. So if I can have to write, and if I can write in terms of the single qubit operator, it essentially I can write it in form of direct product multiplied by the direct product of the identity matrix, whereas for the one state it has to be multiplied by the X or the NOT gate. Okay, so if I can do that, this is one way of representing what we have done from this is the action of the gate. So this is my heart of the operation here. This is what this unitary operator of C0 gate or C0 operator is going to do to my system. Okay, so that is all that is required. The next is how do we express that in some compact form. Okay, this is since you are doing for 2 qubit state, okay, you can write down this thing separately. But as the number of gates increases, then it becomes cumbersome to write in this form. So you require a compact expression, and that is what is being done. And these are two different expressions. One is in terms of the operator. So I can write the C0 operation as the direct outer product of the 0th state into the identity matrix plus the direct product of vector 1 with the NOT gate or the X operation or the what is called as a Pauli X sigma X operation. So, still jump somewhere. Okay. So that is what the C0 get in the matrix form. Then I know that how it is defined. So if you can write this in, because this is what the standard basis of this operator is. So if I write down each of this as column and stack it up, that defines matrix, and that is what is being done. So this is your 0, 0, 0, 1, 1, 0, 1, 1. Okay. If it is an identity matrix, it becomes 0, 0, 1, 0, 0, 0, 0, 0, 1. But in case of C0 gate, this particular matrix is being flipped, which is represented by this vector here operation. Okay. So now, so this is what we have constructed the operation of this representation of the C0 gate. That is what is being done here. So the next task is that you take U dagger C0, multiply the product and ensure that it is going to be I. And it just turns out that also that U square of, C0 get square is also an identity product. Okay, so that is another. Okay. So it is called as idempotent something. So that it's a good thing to know, but not required as such. Okay, so important thing is that it has to be unitary. U dagger U is equal to 1. So if in a very general state, if I is the basis vectors, where I belongs to either 0 or 1. Okay, so now we are writing it in some different form here. The action of C0 gate on the input state ij is written as I into I addition modulo 2 or ij, I plus j, where I plus j is an addition modulus 2. That is 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, and 1 plus 1 is equal to 0. So that is the keyword. Mathematically, in the digit Boolean algebra, it is operation of addition modulo 2, which is your XOR operation. Okay, so these are two examples which you can try to do as an homework here. Show that C0 operation cannot be written as a tensor product of two 1 qubit gates. Okay, you require 2 qubit gates to describe the C0 operation. Okay. So that is the exercise which you can try to do. It's a very simple one. And if you are able to download this book, the advantage of this book is that The solution for all this exercise are given at the end of the chapter, at the end of the book. So you try to can solve it and see for yourself. So I will be doing some extra exercises later on, or I'll give it as I'll circulate that as a note because I don't think I'll get that much time to do things in much detail. Okay. So can anyone quickly do this exercise? The exercise 4.2, A01 plus B1, which is direct product with 0, is an input state to the C0 gate. Okay, so C0 gate is acting on this particular state. What will be the output state? Anyone wants to do quickly, they can try and see, otherwise we'll move forward. Okay, so now we come to because now writing, there's other technique which has been evolved over a period of time about representing these gates in much more graphical way so that you know what is been happening there. So, or what we develop, just like in, we have some symbols for the analog or digital electronics, same concept is extended or extrapolated to the quantum circuits, where we define this line as in the way the data is going to transfer. And whenever you have these square blocks, whatever the operator is going to do, that is mentioned as U or particular gate operation. Any gate operation which is required, which will be carried on this input state, will be mentioned here, and then you have a resultant output which is be available for transmission for further processing. Okay, so as it says, yes, yeah.
So is the answer A00 plus B11?
Yes.
Because the second qubit is the target qubit. So 0, first the A0, 0 is the control qubit, it doesn't change the second qubit. But if the B1, so 1 is the target control qubit, so it will change 0 to 1.
Yeah. A00, B1, correct.
Okay, sir. Thank you.
So,
Okay.
so,
Yeah.
so the input is two separable state, two qubit separable state, and in output is a entangled state also.
Well, it depends on what operations you are going to perform, right? It did not always be entangled.
No, sir, I'm talking about the exercise.
Exercise. Okay, yeah. Okay, yeah, that is true. Yeah.
Oh.
Yeah, that is where the operation is going to be. Yeah, if it is an entangled, then you cannot separate it out. And that's what. Yeah, that is true.
Yeah, the answer he said it is a entangled, so we cannot separate it. 0 plus 1 1, so it's inseparable.
Yeah, 0 plus 1 1. Yeah, that is an entangled. That is right. Okay. So yeah, so now what we are trying to do is we are trying to build out the graphical way of depiction all this gate operations. So it is denoted by the horizontal as the input, then you get acts on it. Whatever the here it is shown unitary operator, any unitary operator which is going to mimic the quantum gate will result in a desirable output. The left horizontal lies the input qubit state, while the right horizontal is the output qubit state. Therefore, the time flows from the left to the right. So this is a convention which we have adopted for this depiction in this quantum circuits and how the quantum algorithms will be divided subsequently. So whatever we have defined as a C0 gate is depicted in the graphical way in this following way. So depending on one bit means one dash line. Second bit means another dash line. So I'm giving an input, so I call as the control bit here. And the second is the target bit on which, depending on its state, this state is going to be flipped. So this is a symbol for an AND. So it is going to perform. So whatever is present here, 0, will be carried on there. It is 1, it will be carried on. So it is just an addition. But here I'm putting as an X, which is something like an XOR gate. Okay, simple, where it shows a conditional negation, or it's a CNOT gate. Okay. So in this CNOT gate, this small dot denotes the control bit, while this denotes the conditional negation. So the resultant output will be, if it is 0 here, it will be 0 there. If it is 0 here, since this is 0, it will continue to be 0 here. If this is 1, this will again be 1. But if this is 1 and if this is 0, then the output will become from 1, it will become 1 here. But this 1 will become 0 there. If this is 0, then this becomes 1. So the output will be 1, 0 or 1, 1. So that is how this entire CNOT gate can be expressed in terms of this graphical symbol here. So we are building some specific symbols for this quantum operations. Okay, so if you want to define, so what CC naught is a control knot. So if I want to have a control unitary operations, I can have instead of this not operation, I can have any other unitary operation, and such a gate is called as control U gate, where this X operator is replaced by that particular unitary operator there, which is the target bit, which is going to be active. So that is the same thing, the designation for this one. Okay, so, and you can have more than one, like required to 1, then this will not occur. Okay, so that is what this CC NOT gate is being built. Okay, so there, and that is what the statement is about control. Okay, so we can now perform. So this is the matrix given for the CNOT gate in this basis. And now you require to find out what is the output here. Okay, so you can see this is, you are building some subsequent adding. So this is a simple gate operation. Here you have developed as a circuit here and a set of instructions. So instruction is following from left to right. So this one is executed first, then whatever the resultant output from the first operation will be used as an input to the second one. And then the second output will be an input to the third one. So you have to do the operation sequentially, and we expect it's going to be linear transformation. So that is what is going to be used to find out the answer for this. So you can try to do this also. Get time. Okay, so follow this 4.123. So this is I was just mentioning about that you can have more than one control. So that is called a CC NOT gate, double control NOT gate. It has 3 inputs, and the third qubit flips only when the first 2 qubits are both in 1. So therefore, I can express that in terms of the operator form as 0, 0 acting with a direct product of 0, 0 plus 0, 1. So this is a computational basis, which is the direct product of the identity, and the II 1, 1 outer product will be negated with the will be the direct product with the NOT gate. So the specific name is given. The person who has devised this control, this CC NOT gate, was Toffoli, and this is also known as Toffoli gate. It's a very, very important gate for reasons which will be coming later when we try to develop algorithm. Now, since we are doing quantum, most of the richness of any quantum mechanical principles are based on its entangled features. Okay, so we require, so working with the separable state is no longer useful because we require to use with the non-separable states. Why? Because the whole basis of creating a measurement or doing on a part of an entangled state is that if I create an entangled pair and I do and separate them, and if I do a measurement on one, automatically I know what is the state of the other. So even without doing a measurement, I know what is the outcome of the other state. So that is my basic advantage of working with this entangled state, because they are directly correlated. There is a correlation between the two states. So how do we create that? So that is because if I take a two-level system, so there is a separable state, there are eigenstates, but I want to create a confusion. I want to create a superposition so that they are non-separable. So to create this, so I require to create a superposition of the states, and that is facilitated by this what is called the Hadamard gate. This is sometimes in literature, you will also see that it is also called as square root of NOT gate. Okay, so that is another terminology which is used to define this Hadamard transformation. So how is it the Hadamard transformation defined? It takes the ground state as a superposition of 0 and 1 state. Okay, in the excitation of 0 and 1. And if it is in the state 1, then it takes in the superposition 0 and minus 1. So therefore, whichever state, initial state the system is in, after the Hadamard operator acts on it, it always creates a superposition of the states, except that there is a slight phase difference of pi between these superposed states. But nevertheless, it creates a superposition of the two states. So from any of the two eigenstates, I can always create a superposed state, and that is where the big advantage, because I would like to make use of all the quantum mechanical features. So the way it is denoted is, the representation is, Hadamard gate is represented as I multiply this by this. So what I'm doing is I'm creating compositional basis states and defining in terms of the matrix. So it is, instead of the unitary matrix 1, 0, 0, 1, Hadamard matrix will be 1, 1, 1, minus 1. The last state is flipped here. Okay, and it is denoted by the letter H. And for any two states, so for all possible 2n states are generated when Hadamard operator is applied on each qubit of the state 0. So I have this Hadamard operator acting on the 0th state, so each one is going to be superposed into 0 plus 1. Okay, so because each one of the 0, H acting on the 0th ground state will result in superposition 0, 1, 0, 1. So that many number of operations are going to perform, so it will be root 2 to the n, and this is nothing but where I have defined this in the terms of x. So therefore, it has created a superposition of all the state x with x0 to 2 raised to n minus 1 simultaneously. This action on n is called as Walsh transformation, Walsh-Hadamard transformation, and it is denoted as this UH acting on W1. W1 is UH.
Sir Lee? Hello?
Looks like Sir lost his network.
Where did I lose? I mean, hello?
So we lost you just now only, sir.
Okay. So what I'm saying is that,
So we lost the presentation too, sir.
okay. Anyway, I'm going to stop now.
Okay, sir.
So up to the Hadamard gate, you can just do those exercises. You can download this book of Quantum Computing by Nakahara.
Sir, I have sent the link in the chat box.
Okay, so anyway, I think, yeah, people can, I think I was logged out, so therefore I lost that link. So people can download that book and use it. Chapter 4, which is what I'm following. But please pay attention to the discussion what we had in this course of how this any measurement or any gate operation is actually going to work. Why this physical significance, or why this? See, what we have done today is that we have looked at the requirement, why the operators have to be linear, why they have to be unitary. So those are the physical basis on which the systems are going to be realized. So uh, you can think about it. If you have any difficulty in or there's some confusion on that, I will try to take it up in the next class. Okay, so right now I will just stop and I will start with the swap or swap gate and Fredinkin gate, and then I will move on to the deviations of criteria, and then we'll take up, if possible, one of the physical system. Okay, so and then request Satya if you can give me one more class, then I will kind of cover one or two more physical systems of quantum computing. So I'll try to take two more classes. Today I got delayed. I don't know. I was not able to log in. But anyway. Yeah. So any other questions that you have? Otherwise, we can call it today. I'm just feeling hungry. That's why to stop.
Sir, no more questions, sir. I had been out of the call for some time, but I think I got up from the linear part. And if I have any other doubts, I'll ask you later, sir.
Okay. Anyone who was throughout with me, do you have anything to say? Comment or? Maharan? Okay, it's fine for me.
No, sir, and towards the linear part, I had no idea why it was important. So now I got some perspective to it.
Yeah. Yeah, you have to question everything. As a physicist, don't assume anything. Though we work on a lot of assumption, but as experimentalist, we require to understand the basis for that assumption. Okay, and why it is there. So that is all that is required to achieve whatever you want to do in the experiments.
Yes, sir. I actually got an exact like how an experimentalist will use the specific terminologies. Like an experimentalist view on the terminologies which we use. Like when we study it mathematically, we just saw it as some abstract things. But like you said, U dagger will make it reversible. I'm taking an example. So those exact like when I can realize physically, like I can see it in hands. So that was the correlation between theory and today's class. Thank you, sir.
Yeah. Good. Okay, anyone else wants to comment something, or we can call it up a day? Okay, then just ponder upon what we have discussed, because the more you think about it, it will be easier to understand the physical system. I mean, you can start examining yourself. If you have not read any of the physically realized quantum systems, what you do is in whatever field you are in, whichever systems you are comfortable with it, okay, from everyday example, and try to ask yourself, can I make of a quantum computer, let's say of even a pendulum, a simple harmonic motion? Ask this kind of questions, because earlier when we started the discussion, I think two of Jesse and Vijit, they were trying to work with polarized light. and trying to make a quantum information processor out of it. Okay. So in principle, theoretically it's possible. Experimentally, we have to see what are the challenges we have to overcome to make it realize as an optical quantum computer. Optical photon computer, it has always been done now thanks to the photonic crystals and nonlinear optics. Okay. Yeah, fine. So then I will stop here and I will try to see that next time this problem doesn't occur. Oh, I think Satya is here now. Okay. Satya, you want to say something or are you there or?
Yeah, I'm there, but